So in the last class, we were discussing about density matrix and how one can represent the different density matrix elements depending on what basis we choose. And we saw that generally how can we use the knowledge of classical statistical mechanics and how it holds in even in case of quantum statistics, but with certain changes, obviously. And it becomes easier to deal with quantum statistics when if we use the density matrix. But that was what we were discussing in the last class. What we will do today is that we'll mostly first look into how the distribution, like how number distribution into different states change, and how that changes the number of microstates depending on whether the particles are distinguishable or indistinguishable, or either there are. So what happens when we have a quantum particle which is by nature indistinguishable, where numbering of the particle does not matter, but then in classical system we can number the particles, and then that can result in different or more number of microstates. So we will look into all these things, that how the density, how the number of microstates change depending on what kind of particles constitute the system. And then we would see that in cases of indistinguishable particles, how we can so in cases of indistinguishable particles, there can arise two kinds of situations. One in which we can have bosons, or on the other hand, we can have fermions, and we'll see what are these and how their occupation number, or which means how these particles distribute into different energy levels, and how that is different for each of them, and how that will change the type of behavior that they show. So we will use those properties to find the grand canonical partition function and see how we can define or find the equation of state from there. So that's how basically this session will go today. Obviously, so I'll give an introduction, and then we will discuss the basic concepts. There'll be some problems, not much, but most of these problems has their solution from the uh, discussion itself. And then if you have any doubt, you can get back to me. Okay. So now, distinguishable and indistinguishable particles. Okay. So what do you mean by distinguishable? That means if you have two particles, you can distinguish. This is particle 1, this is particle 2. While if it is indistinguishable, you cannot number them, you cannot distinguish them. But then even identical particles can be distinguishable, right? If you have, suppose classically, if you think of two identical pens, the two pens are identical, but they're distinguishable. This is one pen, this is another pen. Okay. So suppose if you have held one pen in your right hand and there's another pen on your left hand, though both of them are identical, right? But they are distinguishable. You know that you have this pen in your right hand and this pen in your left hand. So identical particles can also be distinguishable. So this is a basic, a slight misconception that can come in, where we generally think that identical particles are always indistinguishable, but in classical case, that might not be true. Okay. So now consider that you have n distinguishable identical particles in a system of total energy E. Okay. And in this, like this is the total energy of the system is E, but then inside you can have n1 particles in energy level E1, n2 particles in energy level 2, and so on. Okay. So in a way, this tells you that sum of all this n1, n2, n3 dot 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 will give you the total number of particles. And if you do this sum, NiEi, so Ni is the number of particles in energy level with energy Ei, right? So if you do the sum, you'll get the total energy. So these are the two conditions that the system satisfies. But now, given this condition, how many microstates can correspond to energy E with a specified distribution Ni? So what do you mean by specified distribution? That suppose if you are already told, as in the question, that there are N1 particles in the first level, N2 particles in the second level, and this distribution is known to you, you want to see that given this specified distribution, what are the number of microstates that correspond to this energy E, right? So how do you do that? So obviously, because if you have, so this is normal probability or permutation uh, concept, that if you have n particles, the total number of particles are n, and then you are grouping them in groups of n1 particles, n2 particles, dot dot dot. So this is how this will give you the number of microstates, right? Okay, so n factorial divided by product of n I factorial, right? But now, so this is called the statistical weight factor, okay, and it will be defined as or denoted as WNI. Now, in classical physics, where the particles of a given system, even though identical, are regarded as mutually distinguishable, any permutation that brings about an interchange of particles in two different single particle states is recognized to give you a new state. So what I mean by that is that, suppose if you say that the so-called fifth particle is in state Ui and so-called seventh particle is in state Uj, that is distinct from the state where the seventh particle is in state Ui and the fifth particle is in state Uj. So that means permutation or interchanging of the microstate of one particle can give result to an altogether new microstate of the system. Okay. So this happens when you have distinguishable particles. Here the particles can be identical, right? So now, because the particles are identical, we can take into consideration the Gibbs factor. So if you consider the Gibbs factor, what happens is you divide by 1 by n factorial, and what you get is something like this, right? So the only way one can understand the physical basis of this correction. So this question can come in your mind that we always did this 1 by n factorial whenever we were considering that the particles are indistinguishable. But here the particles are distinguishable, and even then you are considering this 1 by n factorial. Why so? See, it's because the particles by themselves, there is an inherent indistinguishability of the particle. So if you have two pens, two identical pens, inherently they are indistinguishable. You cannot recognize them or cannot distinguish them. But depending on where you have placed it, whether you have placed it on your right hand or you have placed it on your left hand, it becomes distinguishable, right? So this inherent indistinguishability of the particles allow you to use the Gibbs factor. But then the particles are distinguishable because by changing their position or by changing their microstate, which defines their system, like the single particle state. So if you interchange that, that gives rise to a new state which you can identify. Okay. So basically, it's like you have two identical pens. By nature or inherently, they are indistinguishable. So you can consider the Gibbs factor. But now, when you are defining a system given that where you have held the pen, so then it becomes distinguishable, because even though each of them are identical, you can say that this is the pen in my right hand and this is the pen in my left hand. So then it becomes distinguishable given your system, like given how you are defining the system. So that's how this thing comes. So here, being identical and being distinguishable is slightly different. So these are distinguishable, and even then they're identical. So because they're identical, you consider the Gibbs factor. But because they are distinguishable, this is how you can define the number of microstates in which you can get this distribution, the given distribution, right? So basically, this would be your statistical weight factor. Okay. Now, what happens if the particles are indistinguishable, right? So according to quantum physics, this situation that we just discussed, it remains unsatisfactory. It's because if they are identical particles strictly, then the interchange among identical particles should not give you any new microstate, right? So in that case, what it means is that whether your fifth particle is in state Ui or your seventh particle is in your state Ui doesn't matter. Okay, what matters is how many particles are there in the various single particle states. Okay, so so initially you had 5 particles in some state and 6 particles in some other state. If that number doesn't change, just by interchanging one particle, like interchanging two particle positions or two single particle states, doesn't give you anything new. That happens when you consider this indistinguishability strictly. That's what happens in quantum physics. Okay, because in quantum physics, you know that, so suppose if you know, that you are always restricted by the Heisenberg uncertainty. So you just know, so given your p or given your momentum, you know that you don't know the particle position better than h cube, right? So that tells you that these particles are indistinguishable. So you cannot identify, if they're identical, they become indistinguishable in that case, right? So what happens then is that what matters is the number of particles, Ni, that how many particles are there in the various single particle states. Okay, which particle is in which single particle state has no relevance, right? So in that case, what happens is that now how many times you do any permutation of the n particles, it doesn't matter. All of them result in the same microstate. So in that case, WQNI, that is this, the weight factor in this case comes out to be 1, right? So now, depending on this property, what property? The property that when you change or when you interchange the positions or interchange the particles, single particle states, whether the microstate changes or it does not change. So depending on this property, how would the wave functions of the systems change? Okay, how will that be represented in the wave functions? So what we mean is that suppose if you have distinguishable particles, we just showed that permutation of particles refers to permutation of variables defining the system. Okay, so suppose this is how you are defining your system. You have n particles and their positions are all of their positions. You are defining the system by the position of the n particles. Okay, so r1, r2, dot dot dot, all n variables are the variables defining your wave function or defining your system. But now what happens is you do a permutation where you have changed the ith particle position with, you have interchanged the ith and the kth particle. Okay, so this is what has happened here. Ri Rk has been interchanged to Rk Ri, right? So now this is, now suppose if they are distinguishable, what it means is that this phi r1 dot 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 ri rk rn is not equal to ri r1 dot dot rk ri rn, right? So interchanging the particles in that case give you a new microstate. It's not the same microstate anymore. That happens when the particles are distinguishable. But now when you have indistinguishable particles, what happens is interchanging this won't give you any new state, right? So that means if you consider this operator as some permutation operator Pik, which results in this pairwise interchange, that would result in the same microstate, right? So when you say that it results in the same microstate, that means on operating the Hamiltonian, it would result the same value. So now if the Hamiltonian is invariant with respect to some change of enumeration of particles, that means this operator, this Pik operator, commutes with H, that is the Hamiltonian. And if they commute, we know that they share the same, you can say the same eigenfunctions. So the eigenfunctions of H will also be the eigenfunctions of Pik. So in that case, we can write that when we operate Pik on some wave function psi, which was initially an eigenfunction of the Hamiltonian, you would get lambda psi, where lambda is some eigenvalue corresponding to this operator Pik, right? So now these are the possible eigenvalues of the operator Pik. What happens now if we operate this operator again? So suppose you have used Pik, that means you have interchanged the ith particle with the kth particle. And then you operate the same operator once again. So what happens? You get back the same state because now you are again interchanging the kth particle with the ith particle. So you get back the same state. So that means p square psi should be equal to psi, which tells you that, so if the initial eigenvalue of pik was lambda, the eigenvalues of p square would be lambda square. And because the states are equal, that means lambda square is equal to 1. So that gives you two values, two possible values of lambda, which is plus minus 1. So that means when you operate this permutation operator, you can get two states. Okay, one is a symmetric wave function where lambda is plus 1. Another is an antisymmetric wave function where lambda is minus 1. Right? Now, depending on whether you are getting plus 1 or minus 1, you will see that that would change how your system behaves when you operate this operator quite a number of times. So suppose your system is, your wave function is symmetric. So that means how many, whatever times you operate the permutation operator, your wave function does not change because the wave eigenvalue is plus 1. So the wave function does not change, right? So in that tells you that now if you have some permutation operator, which is a generalized permutation operator P, okay, which can have n number of permutations possible. So what happens when you operate this operator on some wave function, right? So you can get two kinds of results. One is a symmetric wave function where what would happen is you would always get, obviously there would be a normalization factor in the beginning, but then you would get back the same state, right? But another case is, suppose your wave function was antisymmetric. That means your eigenvalue was minus 1. That means now if you do even number of permutations, you would get the same wave function back. But then if you do odd number of permutations, you would get a minus 1, right? So depending on how your permutation is, if you have an even permutation or a odd permutation, you can get symmetric or antisymmetric wave functions. It is an experimental fact that nature can be described correctly when only by wave functions having well-defined symmetry. Okay, well-defined meaning either it is symmetric or it is antisymmetric. You know for sure that this is the nature of the wave function. Moreover, as experience teaches us that eigenvalue lambda always has the same value for each particle species. Okay, and so it, in one words, this eigenvalues or this nature, the symmetric is the well-defined symmetry that the particle shows or the particle wave function shows is related to the inherent spin of the particle. Okay, so the particles that are described by symmetric wave functions are seen to have integral spin. Okay, and they are called bosons. Well, the particles which have antisymmetric wave functions are called fermions, right? And they have like non-integral spins. Okay, so now let's get back to our same question. What we were looking into was to find out the number of microstates corresponding to some defined macrostate, right? And what we saw is that now if the particles are indistinguishable, it doesn't matter which particle is in which state. What matters is how many particles are there in the various single particle states. Now, can the nature of symmetry of the wave functions that we just discussed, can this nature affect the number distribution? So, in other words, can different particles having different kind of spins, some can have integral spins, some can have non-integral spins. So this inherent nature of the particles, can they affect how they are distributed given some energy levels in some system, right? So first, let us consider particles that are described by antisymmetric wave functions. So by antisymmetric, now we mean that when we do one interchange or interchange of single particle states, what happens is you get a minus 1. The eigenvalue is minus 1. So it changes by a minus sign, right? So that means if you have this operation where you are interchanging two particles, you would get P of psi A would give you minus psi A, right? But now consider that in one state, like in one single particle state, which is defined by some Ri, okay, you have two particles. You initially have two particles, okay. So now what happens when you interchange this two? You get back the same state, right? So because suppose initially what you were doing is you were interchanging Ri with Rk, and you got a minus sign, right? But now suppose you have two Ri, like two Ri variables, meaning that your particles are in the same single particle state. Two particles are in the same single particle state, right? So then if you interchange between them, you don't get this minus sign, right? You get the same state back. So that would give you P of psi A is equal to psi A. Now, if these two conditions have to be satisfied simultaneously, what this tells you? This tells you that psi A is then 0, right? So these two conditions being simultaneously true results in psi equal to 0. That means the wave function vanishes. So this is not physically possible, right? So what is the message that we get from here? We therefore conclude that if a system composed of indistinguishable particles is characterized by antisymmetric wave function, then the particles of the system must all be in different single particle states. Okay, so this is the result which is equivalent to the Pauli exclusion principle of electrons, right? So that means if Ni is the number of particles that are in the ith single particle state, that would be either 0 or 1. So this is what happens when you have antisymmetric wave functions, when you have particles described by antisymmetric wave functions like fermions. But now if you have symmetric wave functions, what happens then? In that case, you don't have these restrictions, okay, because no such problems arise. You're always getting back the same state because the eigenvalue is always 1. So in particular, we have no restriction in the values of Ni. Ni corresponds to the number of particles that are in one particular single particle state. So Ni can be anything from 0 to like uh, infinity. So it can be any value, right? So that means for fermions, Ni can be either 0 or 1. For bosons, Ni can be 0, 1, 2, dot, 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 right? Now, this limitation or this, you can see this condition, which comes from this, the symmetry property of these particles would tell us how this kind of particles get distributed in a system, okay, in a given system with some energy levels, how this kind of particles get distributed. So now consider two different systems, each with three identical non-interacting particles, right? And both have single particle states with energies given as epsilon naught, 3 epsilon naught, and 5 epsilon naught. Now, one system is populated by spin half fermions and other by bosons, right? You want to find the ground state energies of the fermions and the bosons, right? And see what is the difference between the two. So now if you consider, suppose we first consider bosons. What we just learned about bosons is that you can have, you have no limit or you have no condition on the number of particles that can be there in a particular state. So ground state corresponds to the minimum energy possible. So now you have three identical non-interacting particles. So what can happen is that all the three can go to the minimum energy level, right? You have no restriction on how many particles can go to one energy level, right? So that means for a boson, what would happen is your energy would be given as 3 into epsilon naught, because all the three particles would go to the lowest energy that is possible. So it would go to epsilon naught. So the ground state energy in that case would turn out to be 3 epsilon naught. Right. Now what happens for the fermions? Now here you have to consider another thing, that these are spin half fermions. So depending on the spin, there is a degeneracy that comes in, and that degeneracy is given as 2s plus 1, right? Because if you think physically, that means that if it is spin half, so it can be either in the up state or the down state, right? And depending on that, you get a degeneracy in in the microstate, right? So now what happens? So you have three electrons, or you have three spin half particle fermions. So what do you do now? Now in fermions, in one particular microstate, there can be only one particle, right? And then you get this degeneracy of two, which comes because of the spin. So that means now the ground state energy for fermions would be 2 into epsilon naught. So in the ground, in the minimum or the lowest energy level given, that is epsilon naught, you can have two fermions, one with an up spin and another with a down spin. But then you cannot have any more particle there, right? That that is how we always distribute the electrons. That is how electrons are distributed in the different energy levels. So that it satisfies the Pauli exclusion principle. So we just learned that Ni can be 0 or 1. So because you have, and in the same energy level, you get a degeneracy because of the spin. So you can have two particles there. One is a spin up, one is a spin down. And then the other particle has to go to the next energy level that is present. So that means here the ground state energy turns out to be 5 epsilon naught. So now if you find a difference between the two, what you get is 2 epsilon naught, right? So your answer would be 2 epsilon naught, right? So here, whenever you're considering fermions or like in bosons, it doesn't matter because you can have n number of like all the particles in the ground state. You have no restriction. But while dealing with particles with spin, one needs to consider the degeneracy that comes due to spin. Okay, we should remember to include that. Okay. Now, in the next question, you have three identical spin-half fermions, okay, and they are distributed in two non-degenerate distinct energy levels. The question is that how many ways can this be done? So now you have two energy levels, right? You have one energy level and you have two energy level, and you have two spin-half fermions. Each fermions, because of their spin, have a degeneracy of 2s plus 1, that is 2, right? Why? Because each of the fermions can be either in spin up or in spin down state, right? So now what is the total number of states that is available to you? The total number of states is 2. So in each state, suppose if you consider both the states, so you have two states, and then because of the degeneracy of the spin, each particle can be in up or down spin. So that means if what you have to do to find the total number of states possible is 2 into 2. So you have 4 states, right? So total number of degeneracy, or you can say total number of states that are available to you, would turn out to be number of energy states, that is 2, into number of degeneracy due to spin, which is 2. So 2 into 2 gives you 4. And now you have 3 particles. So what are the number of ways in which this can be done? So that is given as 4C3, right? So this is how you would find the number of ways in which you can distribute the spin half fermions, right? Okay, okay, Kamalesh. So till now, what we were trying to do is we were trying to consider the nature of the particles, whether the particles are distinguishable or indistinguishable, and then we wanted to see how, if they're indistinguishable, how depending on whether they are fermions and bosons. So whether that means whether they are defined by symmetric functions or antisymmetric functions, how the distribution of these particles into different energy levels change. So this concept is known to you, right?
Yes, ma'am.
Okay, right. Now, what we will deal with is an ideal gas in quantum mechanical microcanonical ensemble, right? So that means you now have n non-interacting indistinguishable particles in space of volume V, and the total energy of the system is E. We want to find the number of states, okay, number of microstates possible. Now here each energy levels can be, so let us denote the different energy levels as EI, epsilon I, and then for each energy level there are GI levels of degeneracy that is possible, right? And then it is said that in a particular situation you can have n1 particles in the first shell. So first shell signifies the first energy level with the GI degeneracy, or and then you can have n2 particles in the second shell, and so on. So that's how your distribution is supposed to be. So what it means is that now summation over Ni will give you the total number of particles, and this is how the energy levels are distributed. So if this is the first shell here, all of them are energy levels with energy E1, and the degeneracy is G1, and then you have N1 particles in this shell. Similarly, you have the other particles in the different other shells, right? This is the distribution that is given to you, and this is your condition that the system satisfies. So now, because if you have N1 particles in energy level E1, that means if you do a summation over NiEi, it would give you the total energy of the system. What you want to find is omega, which is in a way summation over all the various distributions that correspond to this energy state, or this macro state of the system specified by N, V, and E, and where W and I is the number of distinct microstates associated with this particular distribution that is defined by these values N1, N2, N3, and 4, right? Dot, dot, dot. So now that means Wni in a way is the product of Wi, where Wi is the number of distinct microstates associated with the ith shell of the spectrum. Okay, so that in a way tells you that now in this state, suppose if you now just consider one cell, here you have G1 levels and you have N1 particles, right? And how they can be distributed. So that would define W1. Similarly, you can get W2, W3, and the product of all of them would give you the total number of ways in which you can get this distribution. Now, because they are identical and indistinguishable, the particles can be distributed among the GI levels of GI energy levels given by this relation here. So this comes from the concept of permutation, right? So now when you find the total number of microstates, what you do a product over all such uh, product to consider all such cells, right? And that gives you the total number of distinct microstates that correspond to this particular distribution, right? So this is what happens when you have indistinguishable particles, where you can have n number of particles, like there is no restriction on how many particles can be there in this single particle states. So that gives you uh, the W for bosons, because there in bosons you don't have restriction over how many particles are there in a single particle state, right? This is the case one. Now what happens in case two is that in Fermi-Dirac case, in that case you can have only one particle or no particle in the states, right? So that means no single level can accommodate more than one particle, and that means Ni cannot exceed Gi. So in a way, you can group these GI levels into two subgroups, one which has particles and another which does not have particles, right? So that means the number of ways in which you can have this Ni particles in GI levels can be given as just Gi C Ni, right? And this is what gives you Wi. And then product over all the cells would give you the total you can say the total number of microstates that is possible for this distribution. So this is the expression for the fermions. And the case 3 comes for the classical particles. So in classical particles, the particles are distinguishable. So that means here, if you have N1 particles in some energy level uh, E1, N2 particles in energy levels E2, and dot, 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 and total number of particles are N. That means how many ways can this grouping be done? That grouping can be done in N factorial by N1 factorial, N2 factorial, dot, 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 all the So such that summation over all of this N1, N2, Ni terms would give you N. And then because the particles are identical, we again consider the Gibbs correction factor. So that means what results, what you get as the weightage factor here is 1 by n factorial, Ni factorial, right? And now if you consider one particular shell, in one particular cell, what happens is you have Ni particles, and this Ni particles can be put into any of the Gi levels, right? So that means Wi would be given as Gi to the power Ni. So that here, that means the number of particles or number of microstates for the entire distribution or the specified distribution with Ni particles in state E1, N2 particles in state E2, and Ni particles in state Ei is given by this expression here, right? So this is how the number of microstates can be obtained for the different particles. Now, once you know the number of microstates, you know how to find the entropy. That is just K, L, and omega, right? And here, what happens next is that the term in Wni that contributes the maximum in the entropy is the term which corresponds to the largest number of microstates, right? So we want to find that term. So here Ni star gives you the distribution that has the largest number of microstates. So how do we do that? So we use this Lagrange undetermined multiplier method. So and then so because these are the two conditions that has to be satisfied by the system. Summation over Ni will be equal to capital N, and summation over Ei Ni gives you E, the total energy. So because the system has to satisfy these two given conditions, you have to use the Lagrange multiplier. And then what you see is if you solve this, delta of this term is 0 because you want to maximize the number of microstates. And from there, what you get is something like this. So this is just putting the values using the Stirling approximation. So finally, what you get is this. So Ni star is you can say the state which corresponds to the most probable value of the distribution, right? So one which has the maximum number of microstates, right? And so that means in some particular cell specified by some I, the most probable state would have Ni particles there, right? So Ni by Gi, where Gi, you can see that it takes into account the degeneracy in the system. So this value in a way gives you the most probable value of N in some energy level E, right? And that is given as 1 by e to the power alpha plus beta E plus A. Okay. So alpha and beta are the Lagrange multipliers. So these are the constants. Okay. We have to identify them, and we will see that if you remember your grand canonical partition function, and there we have done exactly the same thing. So if you just correlate, you'll see that alpha is given as mu by kt and beta is given as 1 by kt, and you would see that the value of A now would depend on what kind of particles we choose, right? So then if you put that in the expression for the entropy, this is what you get. Okay. Now this is just rearranging the terms and putting the values of alpha and beta as mu by kt and 1 by kt respectively. So you get something like this, right? So that means that now if you use this expression, you can find the expression for the thermodynamic pressure, and that is given by the term here, right? It involves some steps which I have not done. You can get it in any standard textbooks, or you can even try solving from here. So if you just follow all the steps, you can get an expression for PV, right? Because see, PV is equal to KT into this value, right? And that you can obtain from the expression here. And this is how you get the expression for thermodynamic pressure, right? And now if you remember that PV by KT in grand canonical ensemble could be, we can write it as ln z, where z is the grand canonical partition function. So in a way, this is like a potential, and that would give you all the different thermodynamic quantities. So you can use this relation to find the different thermodynamic quantities or the equation of state, right? Okay. So now that was for a microcanonical ensemble where the energy was fixed. Now what happens if you have a canonical function ensemble? So there your Q is defined as, so Q here denotes the partition function. So that is given as sum over all values of energy e to the power minus beta E, right? So now if you use this relation, you can write it with the, so here G N E is actually the weight factor. Okay, so it's the statistical weight factor for this distribution, and then if you use that, you can write this as the canonical partition function. Okay, so this is the statistical weight factor for the particular distribution set NE. Okay, and then you can now see that for bosons, what happens? For bosons, the weight factor is always 1, right? Because, and so basically these are indistinguishable particles. So the weight factor for indistinguishable particles would be 1. For Fermi Dirac, also it's 1 when Ne is 0 or 1. Now, Ne is the number of particles in one particular single particle state, and that can never be more than 1. You can just have one particle in one single particle state. And if that's not the case, then this becomes 0. This basically tells you that these are fermions where Ni can take only values 0 and 1, and because they're indistinguishable, so the numbering of the particles doesn't matter. So that means the statistical weight factor in that case comes out to be 1, right? And then if you have the Maxwell-Boltzmann distribution, so this holds for classical particles where they are distinguishable, and then there you have this weight factor which is given as 1 by NE factorial, right? So what we will now do is we will put these values and we will see that how our expressions change, how our partitions functions changes for the different kinds of particles, right? So initially statistical weight factor was represented as W of Ni, and here it's written as G of Ni. So don't get confused with degeneracy, which is defined as, which is generally denoted by G. Here it's not degeneracy, here it's the statistical weight factor. So is this clear till here, how you get the statistical weight factor, and why do you get this condition that it's 0 and only 0 and 1 for fermions and any value for the bosons? So all these concepts are clear to you?
Yes, ma'am, it is clear.
Okay. So now we will use this relation. So suppose if you have Maxwell's Boltzmann case, which is for the distinguishable particles, so there you can use this value of the statistical weight factor, and if you include it here and use the multinomial expansion concept, what you see is that you get back the same expression as the classical case, right, as we had previously done. So for free particles, you can just get back the same expression as V by lambda Q, where lambda is the thermal wavelength. So this gives back the same relations as the classical case, right? And for n particles, you have to multiply, you have to have a power of n there, right? And then now if you have a grand canonical partition function, then you have to consider the fugacity term here, because now you can exchange particles. So in that case, we know that this is how, this is the grand canonical partition function, and this is how it's related to the canonical partition function. This e to the power mu by kt is called fugacity, and if you include that, you would get the grand canonical partition function. So that's how here you can write the grand canonical partition function for this kind of particles which satisfy the Boltzmann, Maxwell-Boltzmann distribution, right? But what's more interesting now is to study what happens when you have either the bosons or the fermions, right? And the only difference between them lies in the allowed values of Ni. And the weight factor for both of them would be 1, because both of them are indistinguishable. So now if you put that value, see, first we would just generalize the terms a little bit, and then we would finally put the values of Ni, okay? So this is your general expression, the grand canonical partition function expression, okay? Here, what you can now do is you can write it like this. So what we have basically done here is that we had this e to the power minus beta into this summation. So summation of the exponents can be written as product of the, so summation of the power of the exponents can be written as product of exponents, right? And so that's how we have changed the terms, right? And because z to the power n does not have, do not have the n eat any energy term there, so you can just put it inside, and this is how this can be reframed. So now if you do that, what can now be done is that, see, you have double summation, okay? First over the number n epsilon constrained by some fixed value of total number of n, and then you say that because the particle is, because the ensemble is a grand canonical ensemble, you can have all possible values of n. So equivalently, you can have a summation over all possible values of each n epsilon terms, right? Independent of each other. So that means you can write it like something like this, right? So here you can see that each of these terms can be written independently as a sum over the different n epsilon values, right? So they can take any value from 0 to infinity, because now your constraint over the total number n is relaxed. So if you do that, what we will now do is that for Bose-Einstein case, right, n epsilon can be any value, and for Fermi case, so you can have only n epsilon, like this n0, n1 or n epsilon values is only 0 or 1. So we will put that and we'll see how we get the expression for the partition function. So if you do that for the Fermi-Dirac case, you get something like this. Why? Because it's just e to the power 0 plus z into e to the power minus beta e, because these are the two values that is possible. N can be either 0 or 1. And then you do a product over all possible values of epsilon, so as to consider the 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 freedom of choosing the different energy states, right? So if you do that, this is your Fermi-Dirac distribution. For the Bose-Einstein case, you don't have any restriction. So if you include that, you would get this value for the grand canonical partition functions. This is how the grand canonical partition function looks for bosons and fermions respectively. So now once you get Q, you can find the Q potential, which is given as ln capital Q, right? And this is equal to PV by KT. This has all was initially discussed when we were talking about grand canonical ensembles. So this in a way is a potential that can ultimately give you all the different thermodynamic parameters, right? And also the equation of state. So you can write it like this is, now this too is for the boson and the fermions, and initially we have solved for the Maxwell-Boltzmann case. So if you generalize for all the three cases, you would get something like this, where A now can be -1 for the bosons, +1 for the fermions, and 0 for for the Maxwell-Boltzmann case, right? Depending on what value of A you choose, your potential expression would accordingly change, right? So now once you know the potential, you can also find an expression for the mean number of particles or the mean energy. Okay, so this expressions hold from what we had initially done while talking about fluctuations in grand canonical ensembles, and these were the same relations that we had used. So using the same relation, we are just putting the expression for the grand canonical potential, right? And this is what we get. So the definitions were this, and from there we had got these expressions in terms of the potentials, and we have used those relations here. So now you can write the mean number of particles as sum over epsilon n epsilon. Okay. Now this term here is actually the mean occupation number, which tells you the mean number of particles in some energy state epsilon, right? So this is called the mean occupation number. And here if you put the value of Z, which is given as e to the power mu by KT, and then you get something like this, right? So this is very important, because how your occupation number is, uh, it, it tells you how the numbers get, or how the particles get distributed in the different possible energy states, right? So now this is how, if you plot for the different values of A, which signifies the different types of particles, you would get something like this. So for fermions, you can see that it's never more than 1. Why? Because ni can always be 0 or 1. Okay, so that in a way restricts that it's never more than 1. And so you can see here that for fermions, the mean occupation number never exceeds unity. Okay, because the individual variables are always 0 or 1. And moreover, we see that for epsilon less than mu, right? So if where epsilon less than mu meaning this value, so you can see that it gradually tends towards the maximum possible value, that is 1, right? And now what happens if you have, if you consider the Bose-Einstein case? So the in the Bose-Einstein case, you see that you can have, so for all values of epsilon, your mu should be less than epsilon. So this condition comes from this relation that we had got, right? This relation, this condition. So if you write it as e to the power minus beta epsilon into e to the power minus mu by kt less than 1, that in a way tells you that your mu should always be less than all values of epsilon. And you see that when mu becomes equal to the lowest value of epsilon, some energy, the lowest energy value, that is epsilon naught, which is something you can see here. So there you can see that the occupancy of that particular level is infinitely high. And this is what happens when you have Bose-Einstein condensation. So we'll talk about that in details later, but this is just a qualitative discussion of the mean occupation number for the different kinds of particles. And then if you have the Maxwell-Boltzmann case where A is 0, you get something like this. So this is the familiar form what we generally use, e to the power minus e by kt. So this is the classical kind of nature that we see. And we see that for high temperatures, okay, so when, so this is important to note that while you have these differences in the lower energy levels for high temperatures, so what happens in that case is that all of them merge to the similar kind of values, right? Okay. So this in a way is the condition. So this happens when E minus mu by kt is much, much greater than 1. So exponential of this term is much, much greater than 1. So under this condition, you would get that all the states would come to the same kind of, would show the same kind of behavior. So this in a way is telling you that here the probability of any of the epsilon n epsilon becomes greater than unity is quite negligible, right? And there, this, so the distinction between the classical treatment and the quantum mechanical treatment becomes rather insignificant. Okay, so and so this is what we also see in this figure here, right? So in a way, how you choose your epsilon, or how you choose your so how you choose your chemical potential, or rather how the fugacity value is, can tell you whether it's in the quantum limit or in the classical limit, right? Okay, so now what we will talk about is the statistical fluctuations in n epsilon. Okay, so here this is how you can define the mean occupation number, okay, in terms of the potential, in terms of the canonical function, the grand canonical function, partition function, right? So now if you have to do n square, what do? You have a double derivative, like you do a differentiation twice, right? And so now if you have to define the variance, so this in a way is will give you the fluctuation. So if you consider both of these terms, this is like n epsilon square, and then you have to take a square of this term because it's n epsilon whole square. So if you consider both of that term, that can be written as minus 1 by beta del q whole square of ln q, right? And that means this can be written as minus 1 by beta del epsilon of the mean occupation number, right? This is the same expression as we have here, right? So if you use these relations and then you divide by n square, uh, so the mean of, you can say the second moment, right? N epsilon whole square. So mean of n epsilon, no, okay. So it's square of, what am I saying? Mean of n epsilon whole square, right? So if you do that, so then what you see is it's minus 1 by beta del e of 1 by ne. And this is some expression which in a way will tell you how the statistical fluctuations change with your occupation number, right? Now, depending on what value of A you have, depending on the particles, you can get an expression for different types of particles. So for fermions, A would be 1, for bosons, A would be -1, and for Maxwell-Boltzmann, A would be 0, right? And you see that it matches for the classical case as well when you consider the Maxwell-Boltzmann case. Another thing is to find the probability of n particles in state of energy epsilon, right? So if you look back, so if I look back in this expression here, one second. So if you look back in this expression here, from this is the expression for the grand canonical partition function. So in a way, how does the probability of n number of particles being in some energy state depend? So it has this, it is proportional to this z e to the power minus beta e term, right? Because partition function is in a way summation of all those terms, right? So that means the Pn value that we are trying to look at now is proportional to this term here, z e to the power minus beta e. And then we have to normalize them where we consider the final expression for the partition function, right? So if you do that, you would get something like this. So this is, so P is proportional to Z e to the power minus beta e to the power n. And then when you normalize, considering the different expressions for the partition function, you would get an expression like this. So for Bose-Einstein case, you would multiply by 1 minus Z e to the power minus beta epsilon, because for each term, you have this term here in the denominator. So in order to normalize, you have to multiply by this term, right? And that would give you the expression for the probability of having n particles in some state with energy epsilon, right? Now, what happens when you consider a Fermi-Dirac case? So in the Fermi-Dirac case, you again will have this term, but then now you will multiply by 1 by 1 plus z e to the power minus beta epsilon, right? And this is the expression that you get. What happens now when you have a Maxwell-Boltzmann case? So for the Maxwell-Boltzmann case, P and epsilon obviously will again depend on e to the power minus beta epsilon to the power n. But you again have this 1 by n factorial term, which comes from the statistical weight factor, which is because these are distinguishable particles. So you have that distribution. You did n factorial by n1 factorial, n2 factorial, dot, 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 and then you divided by the Gibbs factor. So what remained, it was just 1 by n factorial, right? And you have to take into account that thing here because now the particles are distinguishable. And then when you normalize for each energy level, what you get, so this is the expression you can see for the from the value of Q for the Maxwell-Boltzmann case. So for each value of energy, you would normalize by e to the power z e to the power minus beta e. So if you do that, this gives you the expression for En. So is this clear till here?
Yes, ma'am.
Okay. So now, till now, we were talking about all the systems and we were trying to find, so whenever we are doing some, you can say, finding the partition function or finding the expression for the potential, we have always involved summations, right? But now if you have a large volume where now the energy levels can be very closely spaced, so in that case, you can replace the summation by integration. And how do you do that? So suppose this is the expression for your, so in terms of summation, now you want to go to a continuous case where so that can happen when the energy levels are very closely spaced. So in that case, you would do a integration something like this, right? So here what you have done is, so integration over all the position coordinates would have given you a volume here, and that gets cancelled, right? Because from here, when you write the expression of P, you have 1 by V which goes down, and then V and V from the integration of the position coordinate gets cancelled, right? So you have integration over the momentum coordinates here, and this is this term here that you have, that you already have here, and then you do an integration from 0 to infinity, right? So if you do integration by parts, this you can see that this term, and so if you put the limits, this would go to 0. So what remains is this term, right? So this is the expression for for pressure, right? Now, you can see that depending on how your energy depends on pressure, or what kind of function your energy is of pressure, this expression for, sorry, not pressure, energy. So how is your expression of energy depending on the momentum? So depending on that, your expression for pressure will change, right? So suppose now if you look at the expression for energy, how do you do an expression? So how do you write energy? So, or the average energy, how will you write that? In terms of the integration, you would write it like something like this, right? Because now 1 by z to the power minus 1 e to the power beta e plus a is the mean occupation number. And then you multiply that with the different values of energy and you do an integration over the entire phase space, right? That gives you the total energy. And if you do that, so now you have again taken V. So the integration over the position coordinate gives you a V out. And then you have 4 pi p squared dp, which is the integration over the momentum coordinates. And you get something like this, right? So in a way, this you can find an value for this integral. And that value is given as h cube e by 4 pi v, right? So we will see that this value would be useful in order to relate the total energy with the pressure. Okay, we'll see how to do that. So now if you look back again at the expression for pressure, you have an integral like this. So consider that you have non-relativistic particles where energy is given as p square by 2m. So that means dE dP can be written as p by m. So in a way, p into dE dP is equal to 2 epsilon. So if you put that value here, you see that now this integral is actually equal to this integral that we just solved. So you can replace this by this value here, and that gives you a relation between pressure and energy, right? This is what happens for a non-relativistic case, correct? Clear till clear? This thing is clear?
Yes, ma'am.
Okay.
Clear.
So now what happens when you have a relativistic case? Can you tell me what happens if you have a relativistic case?
Ma'am, the energy would be equal to P times C,
Hmm.
so that
So if you put
the
that here, what do you get? You have to put that in this expression, right? So you have to put it here.
yes, ma'am.
So try solving and see what you get. You have to use this expression for the integral as well.
Ma'am, I get an integral 0 to infinity P cube dP divided by Z inverse e power
PQ. Okay.
a.
How did you get PQ? See, your energy would be P into C, right? So what would be DEDP?
Ma'am, C.
C. And then what is P into DEDP? P into C.
It's yes, ma'am.
And what is P into C in terms of energy?
Ma'am, epsilon. The,
Right. Yes, right. So that means what you get is you would get an epsilon here, like the energy term, and then you would have just P square dP, right?
yes, ma'am. But the integration is with respect to P, right?
Okay, yes, right. So you don't have to do the integration. So once you got that expression, use this relation. What we want to find is a relation between pressure and the total energy, right? And we saw that this is how, so this integral, you got some integral right like this, right?
Yes, ma'am.
So this can be written in terms of the volume and the energy by this expression. This is what we got from the expression for the energy in the integral form, right? So if you use this relation, you can put this value in that integral and see what you get.
Okay, ma'am.
Where are you stuck?
Um, I think- ma'am,
So
I
did you,
get
tell me.
uh, somewhat like E times C divided by 12V.
Okay, okay, wait. So this is the expression for P you used. Then you had substituted this here. So what you got is some integral like this, right?
Yes, ma'am.
Okay, some integral like this. And in this integral, like you substituted in place of this integral by this value. Did you do that?
Ma'am, the final one.
The
Yes,
final?
ma'am.
So this expression. So
Yes, ma'am.
so you substituted the integral by by the relation here, right? And you had some terms in the beginning, and some of them would get cancelled, right?
Yes, ma'am.
So what remains? So do you get this? Sorry, do you get this E by V term?
Yes, ma'am.
Okay, so and then what you get in the coefficient?
Ma'am, 1 by 3 E by V.
Right. So that's correct. So that's how, so this is a very standard result. For non-relativistic particles, you have this 2 by 3 E by V. This is how the pressure depends on energy by volume. But for relativistic case, what would happen is, now if you substitute it here, you would get something like this, right? So this is a very standard result, right? Now, let us look into, so initially what we had been doing till now is that we were trying to find the expression for the grand canonical partition function using the mean occupation number, and we did a general expression for different, with a term having a, where a can be +1, -1 or 0 depending on what kind of particles we have. Now what we will do is we will deal with the ideal Fermi gas. So that means we are dealing with fermions where A is +1, right? So that means now if you write the expression for PB by KBT, here you would get something like this, right? And the expression for N would be given by this, where 1 by Z to the power -1 e to the power beta E plus 1 is the mean occupation number for fermions. So if you have to write n now in terms of an integral, how will you write that? You will write it by this expression, right? This is the mean occupation number. And then you do an integral over the phase space volume. You divide by h cube for normalization. And so this is how the expression looks, right? Clear, right? Okay, so I think it's clear because it's just we are just, what we had been doing was we are considering the general case. Now we have just substituted the value of A, considering it's a Fermi gas. So now if it's a non-relativistic gas, what happens here is we have energy given as P square by 2m. Okay, so now we want to go from here, the integration is on momentum. We want to go to the energy space, right? So you're doing a substitution or of variables. So if we put that values here, now we have an integral which has epsilon, that is energy, right? So this term 2 pi v by h cube 2m to the power 3 by 2, and then this integral. So this is how n, that is the total number of particles, can be written in terms of an integral which involves energy. So here this term that you see here, like 2 pi v by h cube 2m to the power 3 by 2 root over epsilon by, so this term here is called the density of states. So here the density of states has an epsilon to the power half dependence, right? So it's important to note that this is what is the density of states. But now if you suppose specify that the particle has a spin of half, so that means there'll be an added degeneracy because of the spin. So you have to multiply by 2s plus 1, that is 2 here, right? So in that case, you would have the density of states as 4 pi v by h cube 2m to the power 3 by 2, and then this integral, right? So this is how you are defining n. Now, in that definition, you had this integral. This integral can be written as f of v, or f of nu rather. So f of nu z, right? And that has a form like this. Okay, so it can be expanded in terms of a series. But so ultimately what it means is that now you can solve the integral and you can write it in terms of this variables. So from here, if we use that relation, we get n by v as g by lambda cube f to the like f 3 by 2. That means you have here. So why do you get 3 by 2? Is because you had epsilon to the power half, and that can be written as 3 by 2 minus 1, right? So that's why you get f 3 by 2 z, right? And this g comes because of your degeneracy of the particles. Similarly, you can get an expression for P by KT, and you would get an expression like this. So here you have 5 by 2, right? So G is the weight factor arising due to the internal property or internal structure of particles like spin. So for electron, it would be 2. G would be 2, 2s plus 1. So half s is half, so it's 2. And lambda is the thermal wavelength, right? So now this is how the expressions would look for an ideal Fermi gas. What happens now when we move to low density or high temperatures, right? So if you look at this expression, n by v can be denoted as number density n, small n, right? And so here you can write f of 3 by 2 can be written as n small n into lambda cube by g. What it tells you now is that in the limit of low density, that means n is small, and high temperature, that is T is large, what happens to this value? What would this value tend to? Can you tell me? Any idea how? So if you consider this limit, how will this value change? So what would be the value? Will it be large? Will it be small? What would be this value?
It will be small.
It will be small, right? So it will be very, very small than 1, smaller than 1. So now if Z, so what this in a way tells you is that see F ultimately is a series of powers of Z. So if that is very, very less than 1, that means Z is very, very less than 1. So in a way, you can say that this F nu of Z can be approximated as Z. Okay. And if you use those relations, what you get is this expressions for pressure, internal energy, or the specific heats. So in a way, these expressions are exactly equal or equivalent to classical ideal gas case as we were doing, as we had done previously, right? So this again tells you that in the limit of n lambda cube by g very, very less than 1, we go back to the classical limit, right? Now, what happens in the other end? So when the temperatures are very low, suppose when the temperature tends to 0, what happens there, right? So when temperature tends to 0, you have n lambda cube by g tending to infinity, right? So in under this limit, now if you look at this expression here, what happens? So here, depending on whether your epsilon is less than mu naught is the chemical potential when the system is at t equal to 0. So depending on whether epsilon by epsilon is less than mu naught or greater than mu naught, your power of this exponent would change as uh, you can say 1 by like minus infinity or plus infinity, something like that, right? So in a in a way, so suppose epsilon is less than mu naught. So what it means is that this is a negative term, and then t is very large, right? So you have something like minus 1 by infinity kind of term, right? So in that case, you will have this term would go to 0, and what will you then get is NE, or the mean occupation number, is 1. While when epsilon is greater than mu naught, this term would go to infinity. So then the entire term would go as 1 by infinity, and then NE goes to 0, right? So, so what this tells you, now if you have to plot the mean occupation number, how will it look like? Can you tell me?
Ma'am, kind of a rectangle fills up
Yeah, it
to mu naught.
right. So it's like a step function, right? Something like a step function where you have NE as 1 till epsilon equal to mu naught, and beyond that it's 0. This is what you get when t is equal to 0. Obviously, when t will gradually increase, you will have a distribution that goes something like this, right? So you will have some energy states will also be there for values greater than mu naught, but this is what happens when t is equal to 0, right? So in a way, this value of epsilon naught corresponds to the maximum energy that the system can have, right? And that is called the Fermi energy. So the maximum energy level till which your particles can reside in at 0 temperature is called the Fermi energy of the system. So now if you this was your expression for n. Now what happens at the low temperature limit? What we saw is that the mean occupation number, which is given by this denominator here, goes to 0 for epsilon beyond mu naught, right? So that means now we can do an integration only from 0 to EF, that is the Fermi energy. Only in that region your mean occupation number is non-zero, and that is 1. In all like beyond that it's 0, that means particles don't exist there, right? So then the limit changes from 0 to EF, and then because the occupation number is 1, what you get is an expression like this, right? You can note here that you have this G term here, which so it should have also been here. So this G actually takes into account the degeneracy due to spin, right? So if you have electrons, you would have an extra 2 coming in there. But then now this is how your N is related to the Fermi energy. And if you do some reorganization of the terms, you would get an expression for the Fermi energy, which would look like this. So what this tells you is that now Fermi energy is proportional to n to the power 2/3, where n is the number density given by n by v. All other terms are actually constant. So Fermi energy depends on the number density, and this is how it depends. Now, if you have to find the total energy, right? So we saw that this was the normal expression for I did it somewhere. One second. So something like this. This is how you had done the expression for the total energy, right? Now, if you do this again, what you will get is something like this. Second. So what you will get now is that this total energy of the system can be written in terms of the Fermi energy as 3 by 5 n into Fermi energy, right? If you solve that integral, you will get this value, right? And then you know that we just solved that for non-relativistic particles, T is given as 2 by 2/3 E by V, right? And for relativistic, it was 1/3 E by V. So here we are considering that it's non-relativistic. So that means P is related to E by V by this relation here. So if you put that value, this is your expression for the pressure that you are getting. So can you tell me, how does pressure depend on number density? Looking at this expression, how will your pressure of this Fermi gas system at the temperatures tending to 0 look like? Or rather, here we don't have to consider that the temperature is tending to 0. So the all this limit that we considered was to find this Fermi energy expression. This is a very general result. So how does the pressure of the system depend on the number density? So pressure is written as 2 by 5 n into Fermi energy. So can you tell me what kind of function is pressure in terms of n, small n? It's pretty straightforward. Just look at the expression. So let me tell you, it's because, see, here you have an extra n, and then you have EF, where EF goes as n to the power 2/3, right? And then you have an extra n. So that means how would pressure go? Pressure would go as, so this is n to the power 1 plus 2 by 3, right? So that means pressure is proportional to n to the power 5 by 3, right? Is this thing clear? Okay. So this is the first question that we just now solved, that the pressure of non-relativistic free Fermi gas in 3 dimensions depends at T equal to 0 on the density of fermions as n to the power 5 by 3, right? This is what we just solved. Now, there's another question, is that consider an ideal Fermi gas in a grand canonical ensemble at a constant chemical potential, and the variance of the occupation number of the single particle energy level with the mean occupation number given as n bar is what? So can you tell me what the answer would be? We have discussed this few slides back, but do you remember, or can you tell me what the answer should be? So any idea how to solve this, or what kind of relations are required to solve this question? So maybe if you look at this expression here, you would get some idea. 1 second. Yeah, right. So if you look at this expression here and tell me, so this is your variance, right? And then by n epsilon square. So if you look at this expressions here, what would the solution be? So you can see you have this. So if this is your expression, you want to find variance. So variance is n epsilon square minus n epsilon whole square. So you have to multiply this term up, right? You have to take it in the numerator on the other side. So what you get? You get NE minus A into NE square, NE like average square, right? So then if you take NE common, it would be 1 minus NE, right? Considering A to be 1, which is the case for Fermi energies, right? So if you do that, what will you get? Okay, this is too many slides back, so let me, right. So if you do that, you would get something like this, right? So n, you have taken n as common, and then you have 1 minus n bar, like n bar is your mean occupation number, and then you have 1 minus n bar, right? This is your variance. So this comes from how you can define the different fluctuations in number, or the number fluctuations, how we had defined the number fluctuations in grand canonical ensemble. We have used the same relations, but now we have written the partition function in terms of this mean occupation number, and like accordingly we have solved. So the relations are the same. The expression gives you this value. Okay. So now another question is that if the number density of a free electron gas in 3 dimensions is increased 8 times, its Fermi temperature will be what? So the relation that we have to use is this, right? So here you can see that this is how your Fermi temperature, Fermi energy depends on the number density. Number density is given as capital N by V to the power 2/3, right? So if your number density is increased 8 times, how much does your Fermi temperature increase? So, so how much does your Fermi energy increase? And that, so Fermi temperature is proportional to Fermi energy, so it would increase by the same amount. So you have to use this relation. So can you tell me, if the number density increases 8 times, how much does the Fermi energy increase? So I don't think it should take much time. So see, if it is increasing 8 times, that means n by v has increased 8 times. So if you do 8 to the power 2 third, that many times your Fermi energy should have increased. So 8 to the power 2 third is actually 4. So that means your Fermi energy has increased 4 times. So because Fermi temperature is proportional to Fermi energy, this will increase by a factor of 4, right? Okay. So these were some of the questions. These are very standard questions which come in dealing with Fermi gas. But what's more interesting and what we have to get like used to solving is where the integrals that we were previously discussing, and because that would let you solve for the different thermodynamic parameters or the equation of states. Okay. Now, this is a complete different question which came up in the last class. So, how will the density matrix elements of a harmonic oscillator look in position representation? So, we start with the energy representation and then we see how we can go to the position representation and how does each term of the density matrix look like. So, here, this is your partition function for now here. That means you are doing a stress of e to the power minus beta h is the Hamiltonian, and there, because it's a quantum harmonic oscillator, your energy levels are so your Hamiltonian is defined as minus beta h cut omega n plus half. So if you use this relation and if you do this expansion, you can write it as this term here, 2 sine hyperbolic half of beta h cut omega to the power minus 1. So now this is your partition function. Okay. Now, each density matrix elements in the energy representation, how will that look like? It would look like something like this. So, you're doing this inner product with two different terms, n and n prime, which are the different eigenstates of the in the energy basis. And because they are orthogonal to each other, what you will get is it will get e to the power minus beta epsilon n by z, right? Because when this operator operates on n, you get the value that comes out is e to the power minus beta en by z. And then because they're orthogonal to each other, what you get is delta n n prime. So that means this is the value that you get for each density matrix elements, and they are orthogonal to each other in the energy representation. Now, given this, you want to find how it looks in some other basis, okay, some position representation, which suppose we consider that the eigenbasis or the basis vectors are given as q. So you want to find the elements there. So that means you want to find this inner product, this value, q prime rho q. Now here, if you use this completeness relation, that because the eigen basis or the basis vectors in the energy space were all orthogonal and orthonormal to each other, and they formed a complete set, that means summation over n, outer product of n is equal to identity. And similarly, if you take n prime and do a summation over that, so n and n prime are the dummy variables, so that would also give you one, like identity matrix. So if you use that relation here, what we have done here is we have included this outer product here, outer products of n prime vectors, and we have included another outer product of n vectors. Okay. And then we have summed over them. So this is just multiplying by identity matrix on both sides, right? And then what you see is the factor that we get here is actually this term, right? Pn. So that means we can substitute this term here, and this is what we get. Now, because we get this delta function, that means we can just keep one particular summation, because n would always be equal to n prime only, then this term would be non-zero. So that would give you the final expression, which is given by the expression here. So here z we have replaced by this expression, which is 2 sine hyperbolic beta h cut omega by 2. Okay, so it was in the denominator, we have this minus 1, so it goes up. And then this is the term that comes from this n prime rho n term, and then you have these two inner products which are given here, right? So this was, I think, a question from some previous assignment or something, which Anushka most probably was not able to solve. So this is how it is supposed to be solved. So that's it. So yeah, so thank you. And any particular doubt you can ask me, otherwise we'll call it a day. Okay, so if not, it's fine. So then next day I will be discussing about Bose gas, and then we'll try to solve some questions maybe. So that's it. Okay. So thank you.